In the name of God, I'm Shima Puyan and I'm from University of Zanjan. I'm going to give a presentation about my paper, Significantly Improving Human Detection in Low-Resolution Images by Retraining YOLO version 3. The presentation will be in 4 parts. First, an introduction about human detection. Second part is about our proposed method. Third, we'll talk about our experimental results, and last part covers conclusion. Now, I'd like to talk about the importance of human detection and the challenging of that. Human detection in static images or video sequences has a key role in surveillance and security systems due to its importance in human identification, activity recognition, and crowded scenes analysis. People surveillance in the building or the area is a crucial indicator in sustaining security of a building or area. Besides human detection advances, the solution have some challenges such as different human poses, images size, body structure, camera's angle, intricate background, and low-resolution images. Most of visual surveillance systems, such as camera applications which are using in supermarkets, low-performing applications, traffic monitoring, banks, and etc., cannot provide image sequences with relatively enough resolution, and scenes obtained from surveillance systems have low resolution or small size of persons entered to the places. These challenges affect human detection in computer vision. In reference 10, a method had proposed for human detection in low-resolution infrared videos based on computing edge gradients for each pixel of input images and extracting a model patch of gradient histogram to calculate corresponding histogram vector as a feature vector. Finally, a linear SVM classifier uses to classify each model patch as person or not person. In recent years, deep learning techniques have been widely used in human detection. Higher accuracy and speed of deep learning in comparison with traditional detection algorithms make it a powerful detection method. To detect human presence and location within an image, methods based on a single or multi-layer deep convolutional architecture can be used. In former types of these methods, a convolutional neural network, in brief CNN, have deeper architectures with the capacity of learning more complex features and make them quite different from traditional methods. The region-based convolutional neural network, in brief RCNN, is the former technique which uses neural network for object detection. Due to its vast of computing resources, some improved models such as fast RCNN have been suggested which optimizes classification by building region of interest, pooling layers, and bounding boxes regression tests. On the other hand, despite high detection accuracy of region proposal-based methods, they have complex structure and detection needs more time. Some methods use single feed-forward convolutional neural network, and the location of objects can be directly predicted without any need to region proposal generation and post-classification. Therefore, the structure of these kinds of approach is fast and simple. One of these methods is YOLO, which stands for You Only Look Once. YOLO version 1, 2, and 3 can predict type of an object and its place at an image. In comparison with fast.CNN, the YOLO networks solve the object detection problem by transferring it to a regression problem. The framework of YOLO is darknet, but it has large mistakes in detection of small objects and pedestrian targets in complicated scenes. YOLO version 2 is a framework which normalizes batches on all the convolutional layers of YOLO to regularize the model, removes fully connected layers of YOLO, and adds anchor boxes on it to predict bounding boxes. Next, it has been trained to find better dimensions of boxes automatically using the k-means. It searches the most proper anchor box shapes to find objects easily. YOLO version 2 uses darknet 19 with 19 convolution layers and 5 max pooling layers for feature extraction. But it also suffers issue of small object detection. YOLO version 3 is an additive version of YOLO version 2. It uses darknet 53 for feature extraction and is larger than YOLO version 2 with more accuracy. YOLO V3 has been fine-tuned with upsample features and predicts objects bounding boxes by using logistic regression. YOLO V3 has higher detection accuracy within the image and better performance to detect small objects. YOLO version 3 cannot detect objects in low-resolution images. Okay, now let's move on to the next topic, our proposed method. In this part, the proposed approach for human detection in low-resolution images is described. Low resolution of taken image sequences of closed-circuit television in brief CCTV surveillance cameras makes problems for detecting human by common methods. Decrement of resolution according to the distance increment from cameras mounted in a high position is another reason of need to detect human in low-resolution images. YOLO version 3 uses two sets of images dataset containing Google's OpenImage and COCO. Both have high-resolution images and so that it cannot be used to detect objects in low-resolution images. On the other hand, image sequences recorded by surveillance cameras have low resolution and human cannot be detected within these kinds of images. It means that we use YOLO version 3 to detect humans in low-resolution images, but it does not work properly. So that we need a fine-tuned form of YOLO version 3 to perform better in low-resolution images. Okay, to make improved YOLO version 3 for human detection in low-resolution images, we prepared dataset from real-world image sequences obtained by surveillance cameras mounted in area or buildings. These image sequences gathered from UCF crime dataset and then annotated manually to use them for YOLO version 3 retraining. UCF crime dataset is a set of videos being taken by surveillance cameras mounted within the buildings, and all the videos come from real CCTV cameras and image sequences neither are prank nor manually edited. The dataset has different scenes and it is a state-of-the-art real dataset. Due to these reasons, we use this dataset in our work. After preparing proper low-resolution dataset, we create annotation file of them to retrain YOLO version 3 by low-resolution images. Next, information of the people within the image will be collected by the model based on the detection result achieved by the human detection system. After training process, the model is run on our test images and human detection will achieved. Now, I'd like to talk about our experimental results. To gather a comprehensive dataset, all 109,000 videos converted to image sequences. Afterwards, images with higher differs in human position, images in which people can be seen clearly by human and human can be separated from its background, are chosen from each video sequences. Next, labeling process has been done by using VOTT annotation tool. We specify humans of each images by bounding box manually and label them as person, all as one class. We annotate 100 images containing 309,076 humans. The annotation file is in .csv format. The building of YOLO version 3 model adopted the CRAS 2.2.4 framework based on the TensorFlow 1.15.0 and was modified using darknet 53 framework. To improve human detection detector, the model was retrained on an NVIDIA GeForce RTX 2060 GPU. Taking into account the binary nature of human detection problem in images, samples can be split into 4 types: true positive, false negative, false positive, and true negative. This division is according to detection of human positive mode or misdetection of that negative mode in an image with human true or without human false. Confusion matrix is used for classification results, as you can see in this table. Precision or recall are defined as these equations. Precision is equal to true positive divided on sum of true positive and false positive. Recall is equal to true positive divided on true positive plus false negative. And finally, the performance evaluation is done by F1 score, which is obtained by this equation. F1 is equal to 2 multiple P multiple R divided on P plus R. We calculated performance of proposed method in human detection and compared that with human detection based on YOLO version 3. We computed F1 score by considering intersection over union value is equal to 0.6 for both models, and the results are shown in table. As you can see, the proposed method has been detected humans by F1 score equal to 0.8, and the main YOLO version 3 has been detection result equal to 0.177. In this slide, you can see the curve of precision recall, PR curve, and it's clear that the red graph, which is for our proposed method, is better than the blue graph, which is for main YOLO version 3. Okay, the detection results for retrained YOLO version 3 and main YOLO version are shown in this slide. And you can see the left image is the detection results of our proposed method, and you can see that all the humans in this image have been detected. Despite that, the main YOLO version 3 could not detect the humans of the images, and you can see that just one of them, which is bigger and clearer than the others, has been detected. These figures shows an example of very small, low-resolution human with high complexity in the scene and is detected by the proposed method. The left image could not be detected by main YOLO version 3. The right image, and it is clear that this is a human, but have not been detected by YOLO version 3. From the result of the slides, it can be seen that the proposed method has a good detection effect for low-resolution images, but YOLO version 3 cannot detect human in these kinds of images. This result shows that the improved YOLO version 3 has a good ability to detect human images, which YOLO version 3 could not detect. Lastly, I'd like to look at our conclusion. The proposed method of this paper has demonstrated a system for human detection in low-resolution images by using a new dataset annotated manually, which has been collected from a real-world surveillance image sequences and deep learning, namely YOLO version 3 algorithm. Since the YOLO version 3 detection model was retrained using new dataset, the F1 score of human detection in low-resolution images increased to 0.8. While this system is extended, there are still some problems in detecting humans with high complexity scenes. To increase the F1 score in that kind of images, the dataset used to train the model should be bigger and has higher variety. Therefore, the model can detect human even in complex scenes with even less resolutions. And it can be done in the future. These two slides show my references, and thank you so much for joining me.